Hi everybody, my name is Matwana, and if you first time to this program, please, okay, before we get started, right? Oh, sometime people say, oh, let's start with a prayer. So if you pray a person, please do your prayer, okay? Before you start it, before you do anything, whichever religions that you believe, you could be a Kenyan brother, or if you believe in Yahoo, also pray. If you Muslim or Christian, also you can pray, or any system believe, just get down to it, okay? I'm a spiritual guy too at the same time sometime. So now let's get started because this has nothing to do with this, okay? So before we get started, right, some of you might be new here, right? So please come right here, subscribe to this program, so every time when I upload a new video, you see right here, make sure you click that right there so that every time you can get the notification automatically. You don't miss every time when I upload a new video, and that you're gonna get the notification. Now, so the question here say they say, okay, they say, okay, let's see, excuse me just a second. Okay, so they say here, they say a battery, this is a battery. Okay, where's the battery? This is a battery here because the battery always has internal resistance. You see, they say, okay, that small things here, that's a battery, that other meaning internal resistance. Inside the battery, we have a small internal resistance, which is inside the battery, which is this one here. Okay, excuse me. So now remember, this one here, okay, when you write like this in a circuit, let's say one. Okay, let me write slow. Okay, if somebody start write like this will call a battery. Let's do stuff like that. This is a battery. So now this is gonna be positive and this gonna be negative. Well, there's a longer line means positive, okay, and this is negative. So the electricity is gonna leave here and it's gonna enter here on a negative, and then it's gonna leave on a positive, okay. But if you have a one, this will call cell because only one cell. But this is a battery. Okay, battery means more than one cell, so this positive, this negative. Okay, now let's come to it now. So inside the battery, we always have a internal resistance, means in this is internal resistance. So meaning the electricity, the current is going to be leaving here. Means this current is going to be leaving here. Means it's going to go all the way from the battery here, all the way. See, this is positive. It's going to be moving that way. So now we have a cell and another cell. So these two give us what? A battery. So it means a battery. So the current is going to be moving, and then here is going to be internal resistance. The current is going to be moving. So here, this is ampere. Ampere, it read how many current is going to be passing through this ampere. Now you come here, ampere. This current is going to divide in two parts because this circuit is divisive. So some is going to pass here to the top and some is going to pass to the bottom. But look, when you say resistance, means it resists how many current is passing through. But if you can look careful, this resistance, which you measure in ohm, is 25 ohm, is bigger compared to that. Meaning the current which is going to pass here, obviously, is going to be smaller compared to this. In comparison, this could be bigger. Why? Because there's more resistance here compared to here. It's like, let's say you play sports or whatever, meaning here is bigger resistance compared to this. Means here, smaller current is going to pass, but here is going to be more compared to that. So the current is going to come and then join together, and then we'll have the same current is going to come, but it's not going to pass through because the switch is open. S represents the switch. So if the switch is going to be open, means we won't have a circulation of the current throughout because the switch is open. See? Now, let's go to the question here. So let's say define EMF. So the define EMF, the EMF is the mark. Okay, so EMF you always get inside the battery. See? Is the energy. So EMF is a battery. Let's say this is a battery. Current enter here on a negative and then move. So here we have EMF inside the battery. So EMF, this is energy provided by the work done of a battery. Oh, so the EMF is the energy which is provided by the work done of a battery per coulomb, because EMF, we measure the unit of EMF is what is voltage, but you always get inside the battery. So this is energy provided by a battery per coulomb charger passing through the battery. See, which is what? Per unit coulomb charge of a battery. Okay, so now let's go to 8.2. So let's say EMF. I'm gonna put the definition there very clear. So the EMF Now they say reading for 8.2. Give the reason why the voltmeter. Okay, no. I need to read here. The voltmeter reading. No, the reading on voltmeter was voltmeter. Voltmeter this. So where does it read? Look, this is a battery here because you have the one cell, you have on one cell, and then here you have internal resistance, and there is a this internal resistance R, which is 0.5, very small internal resistance. So now for 8.2, they said the reason for the reading on the voltmeter. So the voltmeter means when you measure this voltmeter at the end of the battery, means on a positive. How do you know positive? Because look, this is bigger, this smaller, means the current go down. So now you measure that. So they say the voltmeter decrease by that when the switch is closed. Means if you close this, so before we close, it seems like the voltmeter was bigger, but now it decreased by what? By 0.5 ohm. Oh, so let me explain clearly. Let me explain here. Easy concept. Look, when the switch was open, means the current is going to be moving here because it's positive. Remember, it's going to be leaving here. So this current was not affected by the internal resistance because it is behind the. Look, let me say it again. This current is going to be leaving here. You see? So the internal resistance is behind where current leaving. How do you know it's leaving? Because this is bigger here. See here, this bigger positive means the current is moving. Move all the way. So when it is open. Now when you close this, means it's going to be effect of the internal resistance. Look, the current question most of the time it differ based on the type of question. Because if you close here, look what happened. Means it's going to come again and the enter here at the cell. But remember, since it's going to come, means it's going to be affecting this one. So the increase or decrease of 0.5 is because of the internal resistance. Because at first, when it was open, like I say, the current will stop only here. It wouldn't pass here. But now the moment you connect means something which has affected the decrease of 0.5 voltage is because it's connected here. So this internal resistance has affected the decrease. Oh, so what that mean? Now let's go to the question here. The question say, give a reason why the voltmeter reading decreased. The voltmeter what? Reading what? Decrease. So the voltmeter reading decreased because, see, because of the effect of internal resistance. See, so what happened with the internal resistance? Because when you, okay, look, the voltage is going to decrease. Why? Because the Coulomb charger is going to be converted to the heat energy. That's the only way. Because look, anything which converted to the heat, see, means then the voltage is gonna decrease. So just because the energy is converted to the heat energy, see, in the battery. Look, that's why sometimes when you use, let's say, a phone or an electric circuit, even a torch, the battery sometimes get hot. It get hot and hot and hot. Why? Because that energy, see, the energy is converted to the heat, see, in the battery. And why? Because of due to the internal resistance. Because look, the current is going to be passing now. So when the current is going to be passing means this resistance is going to start to resist the flow of the current. So when it resists it, the battery is going to get hot and hot and hot. So what happened? Meaning the energy is going to be converted. That energy which is coming is going to be converted to the heat due to the battery internal resistance. So the decrease, like if you want to get an easier way, because here it was open. So the moment it's connected means this internal resistance has effect on it. So how internal resistance is going to affect the decrease of the voltage? Because look, this quantity of charger which is going to be coming is going to be resisted by this internal. When you say resistor, means something which resists. What does it resist? The flow of the current or the charger which is passing through. Because whenever there's a current, there's an electron which is passing. But for now, we don't want to base on electron. This is more of the electricity. So meaning that charger is going to be converted to the heat. That's all. So now I've compiled this definition here, so you can simply just get it. Let me put it for you here. Oh my God, sorry, I got this on here. Oh my god. Okay, so this one here, okay? Okay, and then I'll check it out. So we say for the 8.1, it was question this. So the 8.1, depend term EMF, we got EMF, this EMF, which is this definition. EMF is the maximum energy provide EMF provided the work done by the battery per coulomb passing through it. Okay, so we know. So the work done is the energy. See, or you can say the energy provided by a battery. You can just ignore this one because that's like other way. Energy, you can say the energy or work done. That's what they put bracket. So it could be energy, or you can say work done. The energy provided by the work by a battery per coulomb charge passing through the battery. Okay, or through it. That's the first definition. And for the second one, where they say give a reason why the voltmeter reading is going to decrease for this case, because the effect of internal resistance, because the energy per coulomb is converted to the heat due to the internal resistance. Okay, so that one you got it. 8.2 got it. Okay, excuse me. Okay, so 8.1, 8.2 we're done. Okay, now let's go to oh my god. Oh, my PowerPoint is stopping. Sorry, I'm gonna restart it. Just wait for a second, please. I apologize. I'm gonna just restart in a second, right? You see, it's kind of freezing. Come on, open again. It's coming. Just a second, Family. It's coming down now. No, it's coming. Okay, it's coming back. It's coming back. It's gonna be back soon. It's going back soon. My apology. Okay, he's back. He's back. He's back. He's back. He's back. Okay, we're back. Yo, we're here. Yes, we're here. Cool. My apology, right? Okay, cool. So now the 8.1 we're done. 8.2. Now we go for 8.3. They want the reading in ammeter. Okay, the reading in a ammeter. Reading in ammeter. Okay, cool. So now look, the current you say is going to live here. So we want to know the reading here. So the reading here, look, this is very easy, way easy. So I'm going to say, look, from Ohm's law, we say V equal to IR. Potential difference equal to current times resistance. All right, so now look, we have a lot of information here. We want to know the reading of the ammeter. The ammeter, it read how many or how much of the current which is going to pass. So current which is going to pass equal to, let's make I the subjects here. If you make A the subject, means divided by R, this and this cancel. So current is going to pass equal to V over R. Do you have a V? Oh, yes, we have. What is the voltage? Remember the voltage which is going to be turned to the heat, which is this one. Oh my God, sorry. This one here, that's what we're going to use for now. Okay, for now. So we're going to say 1.5 over voltage over resistance. And the resistance for now is going to be what? Internal resistance. Because you know why? This voltage is the voltage. Okay? Is the voltage which were converted to the heat. No, when internal resistance, when the resistor was resisting the amount of the current which is passing, and then what happened? The charge was converted to the heat, and then that caused the decreasing voltage. So the voltage you're going to use is going to be decreased voltage over resistance. What are resistance? The resistance which caused decrease of the voltage is going to be 0.5 because this is the internal resistance small r. So it's going to be 0.5. And this is going to help us to get the current which we are flowing through this circuit on a phase place. Okay, plug in a calculator. That's going to give us 3 ampere. 3 ampere. So 0.5, 1.5 0.5 equal to 3 ampere. So 3 ampere, when current is out of flow, when the switch is closed now, because they even say here, excuse me, when the switch is what is closed. So now when the switch is closed means now it's closed means the current is going to be passing this way. So here we're going to see 3 ampere. Okay, now let's go to the 3.1. 8.32. The total external resistance of a circuit. Total external resistance is very easy because look how I'm going to get there. Before you go to external resistance, like I say, some of you might be new here, okay? So make sure you come right here, family, please. Subscribe here and share this video, because I'm doing this. And please give me feedback, because if you don't give me feedback, then I don't know, maybe you guys don't like this type of video. But when you give me feedback like, hey, we're trying to look, this video does help. Leave a comments below. Share this video. Especially comments is very, very crucial. Write the comment under. Tell me, like, hey, look, maybe continue make this type of video. This video help my daughter. This video help my son or my neighbor. So I know, okay, this video help. So comments is very, very important, okay? Because I'm doing this for you is the projects. So then I know, okay, it did help them. Okay, now, they want total external resistance. This is very easy. But if you can look careful, these are resistors here. Which resistor flow the current? Resistor 2, resistor 3. But if you can look careful, look. There's something called series arrangement of resistors and parallel arrangement of the resistor. Look, if I have a resistor like this, let's call this resistor 1, resistor 2. If I want to get total of this resistor, let's say resistor 3 also. These resistors are in series. See, series arrangement like next to each other. So we're going to say resistor total. Just add them together. It's going to be resistor 1 plus resistor 2 plus resistor 3. That's how you get the resistor total. But, excuse me, sometimes they don't want to give like that. So they're going to give you parallel arrangement. What is a parallel? Parallel is like let's say like this. That's a first resistor, second resistor, and this is going to be the third resistor. So we got resistor 1, we got resistor 2, and then we got resistor 3. So to get the total resistor here is easy because I'll say 1 over. So now this is how you do when you get total resistor if it's in parallel. You don't do like before, you just add them. No, you do as this. You say 1 over resistor total equal to 1 over resistor 1 plus 1 over resistor 2 plus 1 over resistor 3 plus. So that's how you get the total resistor in a parallel arrangement. Okay, this is called parallel. But the fun and surprising, interesting thing about the resistor, which is arranged in parallel like that, they always share the common voltage. Even though it's a lot of them, but it's in parallel, they use only single voltage. Very, very important this. But the resistor which is in parallel like this, let's say you got something like that. Okay, let's say call this resistor 1, resistor 2. These, they use different voltage. Like this is going to have its own voltage. Let's call it V1. And this one up to there. And this is going to have its voltage, which let's call voltage 2. So that's a funny thing about the voltage in either series or parallel arrangements. So now let's go. So then we're going to say excuse me. So now if you look careful here, look. So we say our current to 3 ampere. Look, this resistor, it came all the way. And then it could, okay, let me stretch. It's like 4 ohm. Look, resistor 1. I'm gonna stretch this stuff. I'm gonna just open everything. Resistor 1. Now it's gonna come all the way. It's series to these 2. It's gonna come. But if you look careful, look, this is resistor 1, right? I'm trying to stretch it up. Okay. Resistor 1, and then it's gonna come, and then what happen here? It's gonna be series to these 2. Oh, so it's like series to these 2. I'm trying to stretch it up, okay? Oh, so resistor 1 is series to resistor 2 and 3, but 2 and 3 are parallel to each other. Resistor 2 and resistor 3. Okay, I see. So meaning this, I'd rather just find the sum of the parallel, and then when I get the sum, and then I'm gonna add with it. Oh, so okay. So let's get now. So say total is the resistance. Let me write here. Let me say resistor external, because they say here find the external resistance of the circuit. Resistance external total equal to okay. Okay, no, you know what I can do? Let me find the resistor parallel phase. So resistor parallel total, this meaning parallel total, you can say P, use the word P, or you can write like that. Resistor parallel total, and then T total equal to, we cannot do that. We say for any parallel, we say 1 over resistor parallel total equal to 1 over, how many resistor parallel? This and that. 1 of the phase resistor, resistor 2, plus 1 over resistor 3, which we know. So we're going to say this is equal to 1 over 25 plus 1 over 15. So 1 over resistor parallel total equal to, I can find the common denominator, 15 times 1 equal to 15 plus 25 times 1 equal to 25 over, multiply these two, 25 times 15. 25 times 15. You see what I'm saying? But this is 1 over resistor total. So what you do now, you can simply plug in the calculator. 15 plus 25, 15 plus 25 is going to give us 40 over 25 times 15. 25 times 15 is going to give us 375. 375. So mathematical, look. So we have 1, so I can just, 1 over resistor parallel total equal to 40 over 375. So what you can do, you can flip everything except the mathematical. Flip, or you can cross. If you don't want to cross, flip it. Okay, flip everything, especially if you have, let's say, 1 over, let's say, let somebody give you 1 over x equal to 1 over, let's say, 5 over 8. You can flip everything. Say x over 1 equal to 8 over 5, acceptable. So x equal to 8 over 5. But only if you have a one group and one group left and right. If you don't want cross multiplication, 8 over 2. So what I'm going to do, I'll flip everything, okay? Then I'm going to say resistor parallel total equal to 375 over 40. 375 over 40. So now then, 375 over 40 is going to give me a parallel resistor equal to 9375. Okay, let's finish up. So the resistor parallel, but when you write your solution, make sure your solution has been in the right order, okay? So when I say resistor parallel total, now it's going to be 375 over 40. 375 over 40, 9.375. But we're not done, because that's only for this. So remember, all these two is series to that one, means they're arranged next to each other. So when the resistor is series, what you do, you add them together. So we're going to say resistor external. Look, why we say resistor external? Because these and these are external of the battery. You see what I'm saying? So we're going to say that one, resistor external total, right here, resistor. Let me just erase this now. So finish up now. So resistor external equal to this 4 ohm plus this, we just got it now, which is 9.375 ohm. Oh, so now this, what we add, because this is series to that, and we say whenever resistors are series to each other, what we do, add. Okay, so the resistor external equal to 13.375 what? Ohm. 13.375 ohm. We're done with that. So we're done with that. Now we want to go for the next one. Let's say EMF for battery. To get EMF is way easy. EMF for battery equal to, you say current times the total of the external resistance plus internal resistance. Make sure it has to be total of external resistance. If you want to write like, if you don't want to write like that, you can say this same as say I times R1. Some books they write like this, so that I want you to understand when you read in the books. You're going to say 1 times R, or you can write like that. And we have everything now because the current flow we have is 4. What is the current flow we had? 3 ohms. We got it over 3 ampere current. Resistor external total, we have this one here. Resistor external total internal equal to 0.5. See? That's all. So you can get the EMF. Okay, so now we're going to say this equal to, or sometimes you can say this, look, multiply in, you can say I, or let's just plug and then I can show another way. What is our current? Current equal to 0.3 ampere. Let's put 3, we're going to put the unit letter. Bracket resistance external total equal to 13.375 plus internal resistance equal to 0.5. Okay, so plug the calculator in our EMF equal to 41,625 voltage. You see, voltage. Okay, for the one we got. Oh, if you don't want to do like that, look, I'm going to show you how you can do. You come back here, you could say I times R, I, that is this external total, plus I times small r, I times small r. So this one is voltage of external, and this is going to be voltage of the internal. Because it's current times from the Ohm's law, V equal to I times R. But remember, this is the internal resistance, and this is a current. So means this is going to give us voltage of the internal resistance. So we could say this meaning what? Voltage, what of the internal, and this is a voltage of the external. Or you can simply say that, because sometimes in the question they might give you, we give you voltage of the external. So voltage external, then you can, so it depends on the question. See, but we're going to do a lot of questions, you're going to get used to that. So V times R, but this is a resistance of external means it's going to give us voltage of external from the Ohm's law, V equal to IR. Same here, V IR, but from the Ohm's law equal to IR means current times the internal resistance. So this is going to give us voltage of the internal, but they didn't give us something voltage of the internal, voltage of the external. If it could be that way, then probably I could come and replace all of this together. So it depends on the question, okay? But for now, there was no need for that because that would be the waste of time. So reading the question is very, very crucial. Okay, so what is our EMF? Our EMF equal to 13. Our EMF equal to 41. EMF equal to 41.625. But our EMF measuring voltage. Now, we want to go to question number, EMF, we have it already. 0.625 voltage. Okay, now let's go to the next question. Remember, current passing it was 3 ampere. We know throughout just 3 ampere. Means this current is 3 ampere. We calculated when you started. Now, they say here, Elena makes the following. He makes the following statement: the current to the resistor R3. They say this current here is larger than the current to the resistor R2. They say here current is going to be bigger than that. Me quickly, even if let's say I don't calculate it, I want to get 1 mark, so we're going to say yes. You know why? If this current is 3 ampere come in, you measure using ampere, you using ammeter, because ammeter is the device which you use this current. But look, if this current is going to come, it's going to split. Some's going to come here and some's going to pass here. But remember here, there's a bigger resistance, which is 25 watt ohm. Means it's going to resist more current to pass. It's going to be more resistance compared to here, because here is just here with the 15 ohm is a little resistance. Is going to resist less compared to the one on top. So obvious here on top, less current is going to pass because more current is going to be resisted by the 25 ohm, which is bigger resistance. But here 15 resistance means way less. So it means more current is going to pass. So quickly, let's say 1 minute left. I'll say yes, it's true. But now let's verify our statement. I'll show you now how we can do that. Look. So I'm going to say, remember we say Okay, we say whenever we have a parallel resistor, they're going to use the same voltage. Like if somebody give, let's say, this resistor, they're in parallel, right? Let's say we got 3 of this. So all these are going to use single voltage because they're in parallel. Only if they're in parallel, but in series, no, it's not like that. Like in series, something like this, let's say. It's not true. In series means each one is going to have its own voltage. Let's call this voltage 1. Say this is resistor 1. And this is going to be voltage 2. Because they're in series. But for parallel, they're all going to use single voltage. So now, let me use that trick now so that I can solve this question. Look here. So we say it's going to use what? Single voltage because they're in parallel. So remember, the current which is going to pass here is going to split. It means some of the current is going to go to the top. This is resistance 2. So let's call this current 2 and let's call current 2 or current 1. But now, do you have a voltage? No, we don't have. So let's find the voltage first, because the voltage, since it is common for both, that voltage is gonna help my life. It's gonna help me right there. So we're gonna say, let me find the voltage with both of these used. So why I want to use that? Because my current. So from Ohm's law, say voltage equal to current times total resistance. So now let me find everything which is gonna pass here. Remember, this is gonna be 3 amperes. It's gonna come and they split. And then it's going to split. Some is going to go to the top and some is going to go to the bottom. Let's call this RC3. It's going to be current 3. And then after it's going to come together and join and move all the way. We remember to say this switch is closed here. Okay. So now let me find the total resistance of these two. Oh, we did already. We said resistance total means 1 over resistor total or resistance parallel equal to 1 over resistance 1, which is 25, plus 1 over resistance 2, which is equal to 15 ohm. And this we're going to say resistor parallel equal to 15 times 1 equal to 15. It means to cross, and then 25 times 1 equal to 25. Yeah. Excuse me. I made a mistake here. Sorry. Remember, it's 1 over resistance parallel. So 1 over resistor parallel. 1 over. Now, take 15 times 1 is going to be 15 plus 25 times 1 equal to 25 over multiply these two. 25 times 15. So we want to get the resistor parallel again because I just erased, so I can't remember. Okay. So now what you're going to do, these two is going to give us 40. And this is going to give us 375 if I'm not mistaken. 15 times 25. Yeah, 375. So what we're going to do, we say 1 over resistor parallel total equal to 40 over 375, and then flip everything. Resistor parallel over 1 equal to 375 over 40. So the resistor parallel equal to 375 divided by 40, 9375. Okay. So this one resistor parallel 9375. Okay, resistor parallel we have total. I'll show you now. We did it before. But I cannot. Okay. So the resistor parallel total parallel, you can say resistor P or resistor double slash resistor parallel equal to 935 ohm, because you measure resistance in ohm. Okay, so we get the resistor total here. Okay, so now remember also, I know the current in total because the current come here, and what happened? This current is going to come with 3 ampere, right? It's going to come ampere and then split, and then it's going to come together. So the total of the current was 3 ampere. So the current total equal to 3 ampere. Let me find the voltage, because I know the voltage is going to be common for right and under. So we're going to say voltage from the Ohm's law, voltage equal to I R. Current total of everything I have 3 ohm times resistor total I have, because these were parallel, which I just calculate now, which equal to 9.375 ohm. And if you multiply these two, it's going to give me 28. It's going to give me 28. Okay. 0.125, 28.125 voltage. Oh, so these two, they're gonna share the same voltage, which is what? 28.125 voltage. Both of them, because they're in parallel, means the resistor at the bottom and the top is going to use the same voltage, single voltage. Now, make sure you write everything if you write your solution. Now, let's go. Okay. So we got voltage, they're going to use common, write everything, right? Resistor 1, resistor 2, current, we only know the current which is total come here. Look, this current is going to split, means this is going to be current T, this is resistor 2, current 2, and the sum is going to come here, it's going to be current T 3. So we want to know by calculating to show that this is going to be smaller than that, because they say show here R3 later. Let's start R2 and solve the current 2, and then after that, get current 3, and then we're going to compare. From Ohm's law, V equal to I R. But this can be current 3. No, let's start with the 2, we say, right? Or either the 2, okay. And this can be resistor 2. So voltage we know, which is that on 28.125. Current, we're looking for that to see if it's true. Now, resistor 2, we do have equal to, what is resistor 2? 25, okay? So then we want to find the current. Make the current subject divided by resistor 2 divided by resistor 2. This and this cancel. So current 2 equal to voltage, which we have in common, 28.125 over resistor 2. What is the resistor 2? 25 ohm. Plug in the calculator. If you plug in the calculator, it's going to give us 112.5. It's going to give us 1.12 ampere. Oh, so these 3, if it comes, going to split. Some is going to pass at the top, which is going to be 1. Okay, let me write here. It's going to be current 1, current 2. I mean the one which is passed on top, because this is resistor 2. So this is going to be current 2 equal to 1.125 watt ampere. Okay, so now we want to get to current 3. I can use the same method, or I can simply say, take the total current, which is what? Which is 3 ampere, which was coming here, and then minus the one which passed to the top. See what I'm saying? So I can say 3 ampere to get current 3 equal to 3 ampere minus, because look, this current came here, which is 3 ampere, and then it went and split. So sum the one which on top is 1.125 ampere. So if I want to get this, means take total minus that, and then I'll get the one at the bottom. So I can say 3A minus 1.125 ampere. Okay. Okay, plug this in the calculator. So I can simply say 3. Okay, so I'll say 3 minus 1.125. Oh my god, 1.12. Yeah. SD. So 1.875. 1.875. 1.875. Okay, 1.875. Come back here. 1.875. So then we're going to say current 3 equal to 1.875 ampere. You see what I'm saying? 1.875 ampere. So this is going to pass in at 3. So let's compare now. The one which is passed at the top is this one here. 1.125 ampere. And the one at the bottom is going to be 1.875 ampere. So we see the one at the bottom is bigger compared to, because this is 1.875 and this is 1.12 ampere. So this is bigger. See, so the statement is true, because here they say the current through the resistor 3 is larger than the current through the resistor 2. Yes, it's true. And like I said from beginning, even by looking, you can see, like, okay, look, this is 15. This is 25 resistor ohm. Means more current is going to be resisted here. That's why more current is going to be resistors, it is going to be resisted, because here there's a more resistor. Resistor is something which resists the flow of the current. So here is going to be resisting it passing, but here is less resistor. So here, that's why this is the current passing is going to be smaller compared to the one what passed through here. See? Okay. So okay. Now let's go to the last question. So the last question here, let's say it's very easy here, man. The last one's here. They say, okay, the learner makes it, man. So it's yes, it's true. Like how we say, the current or through the resistor R3 is larger compared to the current which pass here, but we have to show the proof. Now the last one, they say the resistor 4 means they decided to remove this resistor. But remember, this external resistor, same as this. They're outside the battery. So that's why we call them external resistors. Now, how would that affect the EMF of a battery? It's not going to affect the EMF of a battery because they're outside of the battery. Those are external resistors. So for that case, they say the EMF of a battery, how it's going to be affected. Choose increase, decrease, or stay the same. It's going to remain the same because the EMF is inside the battery. We get it in a battery. So it was not affected because removing this 4, see, removing this 4 ohm, it does not have any effect on internal battery. Okay, so the answer is going to be, is going to remain the same. So look, like I say, man, if you FaceTime in this program, please give me feedback. Because when you give me the feedback, then I know exactly what you guys going through. Like, hey, I'm trying to look, maybe I suggest do like this. Or I'm trying to listen, I'm trying to coach, do this, okay? So look, man, look here, man. I love my brothers and sisters from the country. This me right here, I didn't show you this. Come here, subscribe please to our program and share this video. I'm trying to Battle Academy, subscribe and share this video. And on the top of that, oh my God, this is me right here when I was 4th grade with my friend. His name is Amar. See, and this is my friend too. And this is a Rasta guy, you know. He was bigger than us at that time, you know. See, we call him brother. He's a Ras. And I got this, my friend too, man. You know, we grew up together, all these, okay? So this is me right there. I was a little baby. That's my mom and her friend. They got the African look in our African drum here. I love my brother and sister. So if you have any question, please leave a comment. Tell me what you suggest. If this video was very helpful to you, leave a comment. Say, Mutwana, this video was helpful. Oh, Mutwana suggest this, okay? Because I do this for you. So give me the feedback. It's very, very important. So I know, okay, maybe this type of video helping you. Maybe I can make more. Maybe I should do that because this is our program, okay? It's me and you, so you can benefit. Peace, and I'll see you soon. I'm out.